And hi, everybody. This is Joanne with Read Science, along with my co-host Jeff Schomeyer, and we are very excited today because we are talking about Mars. There's been a lot of buzz about Mars, and we have a couple of experts with us who not only, in addition to all the science they do a lot of communicating about science, and that includes writing books, writing short documentaries, writing articles for the general public, in addition to their proper scientific work with NASA. Today we are joined by Jim Green, the director of the Division of Planetary Sciences with NASA. And Jeff will introduce him more fully. Jim, go ahead and say hi to our audience.
Hi.
And we are also joined by the primary investigator for the MAVEN mission to Mars, Bruce Jakosky. Will you say hi?
Hi, Joanne. Real pleasure to be here today.
Glad you guys could join us. And Bruce, we actually have a physical book in our hands. He's the author of this book, Science, Society, and the Search for Life in the Universe. So this is our connection to Read Science. But Jim also was a consultant for the movie The Martian, which of course is based on a book. So I assume some of you have tuned in. The book is, of course, nonfiction, although I've heard rumors of people thinking it was based on a true story. So you guys set us straight. Have we gone to Mars yet? What are we trying to do there, right? Okay.
Well, we are on Mars.
We are. That is true. Jeff, go ahead and introduce our.
Yeah, you're giving away all of my best written material here.
You know how I like to do that.
So it's my pleasure to introduce Dr. James Green, the director of NASA's Planetary Science Division, a position that he's held for about 10 years now. He got his PhD in space physics from the University of Iowa, famously, for me at least, the home of the late James Van Allen. And he got his degree at about the time I graduated from Cornell College, which was just up the road from where he was. He started working at NASA at the Marshall Space Flight Center in Huntsville, Alabama, where, among other things, I was very interested to read that he was a safety diver in their famous neutral buoyancy tank. In 1985, he moved to Goddard Space Flight Center, which is very near where I'm sitting right at this moment. He abandoned the suburbs of Maryland for downtown Washington, D.C., and NASA headquarters in 2006. Wikipedia also told me that he is an authority in Civil War ballooning, which reminds me to mention that the first recorded balloon ascension in America took place in Bladensburg, Maryland, which is about halfway between my house and Jim's office in Washington. He was also the science advisor, as Joanne said, for the current movie, The Martian. Jim, we're very happy that your schedule let us join you, and welcome to Read Science.
My pleasure.
Joanne.
Yes. Okay. You know what? You said I'm stealing all your information, but look at what the connection you made. I was like, wait a minute here. I can't possibly. But that doesn't beat the time that I discovered one of our guests also modeled in Japan like I did. So I suppose
it's fair. It's fair.
It's fair. Okay, so I am really thrilled today to introduce Bruce Jakosky, because I've been involved with the new media workshops that have been held at the University of Colorado surrounding the MAVEN to Mars mission, and I'm going to let Bruce tell us exactly what the MAVEN mission did. I did learn something when I was there, but I'm just going to let Bruce, since he is actually here virtually. Bruce is so as I said, at the University of Colorado, he teaches undergraduate and graduate courses in both Earth and planetary geology and extraterrestrial life, including both the science and the societal and philosophical issues relating to the science, which is one reason we're so excited to have you on the show. His research interests are in the geology of planetary surfaces, the evolution of the Martian atmosphere and climate. That's the purpose of MAVEN, the potential for life on Mars and elsewhere, and the philosophical and societal issues in astrobiology, all of which are touched upon in his book here. He has been involved with the Viking, Solar Mesosphere Explorer, Clementine, Mars Observer, Mars Global Surveyor, Mars Odyssey, and Mars Science Laboratory spacecraft missions, and is involved in planning future spacecraft missions. He heads up the University of Colorado's team in the NASA Astrobiology Institute. He has published more than 100 papers in refereed scientific literature. His book, The Search for Life on Other Planets, was published in 1998. And, I'm sorry, that's the next one is Science, Society, and the Search for Life in the Universe was published in 2006. I'm sorry, I mixed that up. Okay, these books are hard to find, but you can find them, folks. So if, after today you want to read them, they are findable. It's just not as easy as you think. So he serves on numerous national advisory committees and serves as the Associate Director for Science in the Laboratory for Atmospheric and Space Physics at the University of Colorado. That's the LASP that helped host all of us new media folk, which has been a great experience for me. So Bruce, welcome.
Thank you. Like I say, it's a real pleasure to be here today.
Great, we're so glad. Okay, Jeff, you go first.
Well, I couldn't decide. I had two questions in mind, and I've just changed my mind about where I wanted to start because I think Jim and Bruce. This was originally a question for Bruce, but I think Jim will have some insights to offer too. So I want to ask Bruce if you'd start. I'd like to hear for me and for the audience your elevator talk, your short sketch of what the science mission is for the MAVEN mission, but with a purpose, because then I'd like you to choose one of the instruments on board as an example and give us some insight into the connection of how you engineer, choose something, how you go about selecting measurements that you can make and get an instrument into the orbit of Mars, and how that's related to doing the science that you said you would be doing. And then we're going to come back to explorations and planetary things, and Jim then can offer some input on that too. Easy.
And for all of that, I have just the elevator speech.
I thought you might.
The MAVEN mission is really all about learning about the history of the climate of Mars, the history of the atmosphere. We have a lot of evidence from all the previous missions that the climate on Mars has changed over the last several billion years from one that allowed liquid water to have been present early on, but in today's environment, liquid water is not stable. So why did that change occur? Where did the water go? Where did the CO2 go? MAVEN is orbiting the planet, studying the top of the atmosphere, and we're trying to learn about the ways in which the sun and the solar wind can strip gas off the atmosphere and remove it to space. So we're testing the hypothesis, if you will, that the Mars atmosphere has been lost to space throughout time. We think that it may have been a dominant mechanism or certainly an important mechanism for climate change, and we're trying to quantify that. When we set out to do the mission, we thought, what are the types of measurements that would allow us to understand that? What are the processes we want to measure, and what measurements can we make that would tell us how they work? And we had to look at what instruments are out there. You can't design a mission from scratch with truly a blank sheet of paper. You have to have some idea of what capabilities you can draw on. And I'll use one example, what we call the static instrument, the superthermal and thermal ion composition instrument. It was built at UC Berkeley. They're one of the major partners for us. And it was based on a lot of earlier instruments that have been built, but with some modifications. It's an instrument that measures the composition, speed, and direction of ions. And we're using it to look at how ions are stripped away from the atmosphere by the impinging solar wind. So let me stop there, Jeff, and see if you want to go any direction from that.
Yeah, a quick one from that. So is that then tied back for looking at a mechanism, one of the mechanisms that you could then use to build models and understanding of the loss of the atmosphere?
Exactly. Because we can't make measurements at all times surrounding Mars, and in particular, we can't make it 4 billion years ago when all the action was really taking place. What we're trying to do is look at the very small rates of loss today and understand the processes, and then ask how those processes change through time and how they might have acted 4 billion years ago, and that will tell us what happened early on.
All right, so I'm trying to understand the connection between these engineering marvels and science, and then how these particular measurements do that. And part of that question, Jim, I think you might be in the right position to say, how does a mission like this specific one get selected and off the drawing boards and into orbit around Mars versus all of the competing ideas that scientists have in various places?
Well, you know, there's so much we want to know about Mars. And so the community has to get together on a regular basis and discuss what the most important questions are that we want to answer. And these are really very well related. When we look at our planets today, we really are looking at them in a snapshot in time. But by getting down to the surface and looking at the geology and its history, and then by going after the mechanisms that have obviously changed on Mars over time, as other mechanisms are changing all the other planets, there's a lot of connectedness. For instance, Curiosity, which landed on Mars in 2011, it's been there many years now, or launched in 2011, landed in 2012. We now know it's landing in an area for which there was a significant amount of water, perhaps 3 billion years ago. For tens of thousands, maybe several 100,000 years. And so Mars in its past was very different than what we see it today. You know, it looked more Earth-like at that time than it does today. And so MAVEN is just the right mission to look at what are the mechanisms that operate over time that may have contributed to the global change on Mars. And in fact, is that global change that occurred on Mars something that happened quickly or took a long time? Those are some of the questions we would like to answer. And so MAVEN actually is a perfect follow-on to what we're finding about Curiosity. But MAVEN-like mission had been desired for actually more than another decade. So even in the Planetary decadal that came out in 2001 or 2002, an atmospheric mission like MAVEN was one of the top priorities. And so it takes a long time to get these together. It takes a long time to really pull the teams together that have the right ability, the right instruments to make the measurements that enable us to answer the questions. And that's what our PIs have to do. And it's very competitive. When we ask for proposals, we get you know, several tens of proposals at times. And then we have to go through a peer review evaluation. Then that comes to a selection. Not everyone can win, and the most well thought out mission actually is the one that we want to execute, and MAVEN certainly is that mission at Mars today.
Yeah, well, I remember one thing that was emphasized over and over was how this mission was on time, on budget, or slightly under. How often does that happen? And they did that even with the government shutdown. They managed to get through. So is this amazing or what?
Well, you know, from a NASA perspective, when we get to the point of going from the proposal and getting it into a stage for which we then give the nod to the investigator, start building it, we recognize that there's a certain percentage of those missions, and we hope it's only, you know, a few, that are going to go over budget. And so we really work hard to help the teams and provide what they need in terms of their funding and schedule and resources and everything that I can do to help Bruce make that a reality. And of course, Bruce has done a fabulous job. You know, he's one of my top PIs. I will say it that way. In honoring his commitments and getting this mission under budget, off the ground at the right time. and it's doing fabulous. I really love the science, as Bruce knows, about what it's doing.
Behind the scenes, there's a lengthy process of workshops and winnowing and discussion and refining of the questions and proposal sequences and more proposals and reviews and things. So Bruce, keep smiling and tell us how many years it took. And where, you know, from wherever you want to say the beginning of this went on, but it takes decades. And
I'm going to go back a little farther than Jim did. The idea of a MAVEN-like mission at Mars really goes back to the mid-1980s when a study group put together a scientific rationale for flying this kind of a mission and put together a straw man payload. MAVEN actually looks a lot like that mission. Our team, though, we decided in 2003, so that's 12 years ago, we knew that there was going to be an upcoming opportunity to write a proposal to fly a mission to Mars. And we decided that we thought a mission like this could be competitive and would address high priority quality science. And we started planning in 2003. The original proposal went in 2006. We were selected for development for flight, which is what Jim was referring to, in 2008. And from then until launch in 2013 was almost a straight shot of really intense work. So our team has been together for a dozen years so far. We've been in orbit now just over 1 year, and we're coming up on the end of our primary science mission. Once we commissioned the spacecraft, we were approved for a 1-year mission, 1 Earth year mission. We're coming up on the end of that in about a month, and we've been approved now for an initial extended mission because we are doing good science and we can continue to do good science. But we're looking beyond that. We think we have enough fuel that if nothing breaks, we can survive a decade or longer in orbit and do high-quality science. By the time we get there, we're talking about a team that will have been together for more than 20 years. That's half of a career. It's a major investment to commit to doing a mission like this.
One last little administrative detail to fill out that picture. Between you and your team and the instruments and their teams, all the payload aspects, the subcontractor who built the instrument, the NASA centers that operate and fly and launch. So give us an idea how many people are involved in getting the MAVEN spacecraft into orbit around Mars.
I think if you counted up noses, rather than what people call FTEs, factions of people, there are about 500 people that have worked on MAVEN. Today, we have about 125 members of the science team who are doing analysis of data and operations, and about another 40 or 50 who are focused on the operations. And that leaves out people who staff the Deep Space Network, people who built the launch vehicle, because I don't know how many that takes. It's provided to us. A lot of people have made a major investment in getting MAVEN there. And one of the things that I realized actually only recently, when I talked to the engineers who helped build the spacecraft, they think this is absolutely the coolest thing they can be doing with their careers. And I think that really holds across the entire team.
I saw that when I was doing microgravity sciences, that nobody was in it for the money. Everyone was doing it because they really got a charge, a professional and personal charge out of working on space things. Anything to add to that process, Jim, then, before Joanne gets a turn?
Yeah, I've also, before I came to NASA headquarters, was not only part of several proposals, some of which won, but also a PI on a failed proposal, and it's an enormous effort. You really put your heart and soul in it, and it is unfortunate that we can't pick more missions because, you know, from my perspective, the solar system is really we're just scratching the surface of the discoveries that we're making, and I want to make more, and I want to make them more rapidly, but there's a certain budget and a certain pace that we have to go at, and it's just tremendously competitive. And so our PIs are, just our top people in the community that work so hard to be able to bring their ideas into fruition, and that's non-trivial. It really is a great adventure for those that are part of it, and for the sake of the country and what we learn it's vital, I think, that we understand the environment that we're in, and that includes our planetary environment in a major way.
Yeah, that'll bring me back to something I want to do later, but Joanne gets to change the subject, I think.
Yeah, actually. There's a couple things that have been exciting recently, and I think NASA's been able to take advantage of the enthusiasm about the new movie, The Martian, which is nonfiction, or nonfiction, it's science fiction, duh. Gosh, it's so convincing. No, it's science fiction, and was turned into a movie because, as everyone called it, it was sort of a Robinson Crusoe story of an astronaut left behind on Mars. And believe me, when that book came out as a, as a proper book, because it first was being published as a blog post and then as an ebook, cheap ebook, and then when Random House said, can we publish this? When that came out, I got so many messages across all social media, you have to read this book, and I'm glad I did. I mean, I was crushing under the weight of the messages to read the book, and I really enjoyed the book. I couldn't say for sure how much of it was really real, but then when I heard who would be involved with the movie, I was even more excited. So I've read the book, and I've watched the movie, and then I was happy because I'm like, oh, I know so many people who, I've interacted with people who are consultants on the movie, and Jim, you are one of them. So my first question is, which was cheaper to make, the movie or to send MAVEN to Mars?
Well, really
are we spending our money properly? That's what I want to know.
But how I got involved is, when you read science fiction or any book, your mind really paints that beautiful picture of what you're reading, and you have a natural affinity, if you keep reading it and enjoy it, to paint that beautiful picture. But a director who gets the job of putting that on screen has really got to paint that picture for you. And so in May of last year, Ridley Scott called NASA headquarters and talked to the public affairs official that is involved in the entertainment business, and that's Bert Ulrich, and asked Bert, I need to talk to somebody that knows something about Mars. Okay, so that would be me, and I was in the cafeteria at the time, and I walk out of the cafeteria, and Bert is running all over NASA headquarters looking for me, comes up to me, and he says, can you talk to Ridley Scott at 2 o'clock? And I said, the Ridley Scott? And he said, yes. And I said, absolutely, I'll clear my calendar. So I hadn't read the book at the time, but the conversation with Ridley, which was about an hour and a half long, was really all about what is Mars really like? What about the dust storms? What about radioisotope power systems? What about ion engines? Everything you can imagine. And so I answered about half these questions, and I hesitated guessing at the rest. So I said, well, what I need to do is really connect you with some experts in the agency. And so after the phone call that weekend, I read the book, and then, man, I was pretty excited about it. It really was going to take something that has a lot of basic aspects about it that ring true to me, and then put it on the screen. I wanted to be able to help him, and I got the approval from NASA headquarters to do that, to be a consultant. And so we started interacting back and forth. We had another telecon. I organized a trip to JSC. Then there was another trip to JPL. I farmed out questions all over the place. I took the ones that I could answer, that I wanted to answer, and then farmed out the rest, and then we collected them and got them back to them. And so there was a pretty intense 3 or 4 month period of back and forth, almost weekly or every other week, even down to what does the screens look like in a control room, and can I get screen captures? And so we were sending him all kinds of stuff. What does Mars look like? What about this area? What about that area? And so he's taking those images and then trying to find some place in the world that looks like that. And he did a fabulous job. Overall, I think it's very stunning. It has a lot of beautiful aspects about it. And then, of course, it gives me an opportunity when the movie really comes up to really talk about what Mars is like. And it's easy to make comparisons. From we use radioisotope power systems, and we're developing ion engines. In fact, we're using them now. These how they work. So the questions we get are all about how those technologies are used and what Mars is really like. And I think that kind of exchange, having the opportunity to tell not a science fiction story, but a science fact story, is really a delight. And I've enjoyed it over the last year doing that off and on.
Especially since not every director or producer seems to have a commitment to accuracy and precision in the science. That's really a delight to hear.
Yeah.
So I actually got to read a couple scripts, and and I would make comments on them, and I actually stopped doing that after the first, maybe 2 rounds of that, for the simple reason I recognized that although they took only a couple of my suggestions that were actually relatively minor, that they were really going to try to stick to the book.
Yes.
And so it was really up to us to be able to help him paint that picture. That's really where we stepped in. So, I've talked to many of the actors. So Mackenzie Davis, who plays Mindy Park, and we were talking about, well, how easy was it to play that part, and she loved it because Ridley didn't have green screens on the screens on the telemetry screens. He really had either the JPEGs we sent them or they created data. And so they had real things to look at. And so she said it was great. It was easy for me to point to this and look at that and remember what I want to say. That's another great thing about how the movie was done. Ridley actually only used a few green screens. They literally created the rovers and the HABs and built everything. And so it had a great look and feel about it. It wasn't fake.
That's great. So, Bruce, I take it you read the book and watched the movie. What did you think?
I think Jim had a very positive influence because, for the most part, it was both very close to our understanding of Mars and a really engaging film. I did notice maybe half a dozen areas where I think they got it wrong or missed the boat a little bit, but that's beside the point. That's not the purpose of the movie, so I'm not even going to tell you what they were. I will tell you what I noticed, though, that is also part of this being an adventure, Robinson Crusoe on Mars. It's that throughout the whole discussion, the whole movie, we never knew why they were there. The why came up 2 times in the movie. At the very beginning, we see Matt Damon collecting samples, and I, as a scientist, imagine that he's doing it for scientific purposes, but it's never talked about. And then at the end, I love the scene where they are talking about the next mission, and they get a question from a reporter of what is the purpose, what are the goals of this next mission going to be? And the answer was same as the previous one. So they never talked about why we're doing it. And again, that's part of the story. It's a human drama, and the science is the background, not the central point.
Right. Which,
so in reality, the very first script had Matt Damon away from the crew coring rock, and I really liked that. and you know, he was doing the science, and you were seeing it, man. And the second version of the script, they modified that such that he was closer to the rest of the crew, and then ended up being part of the party that then went to the rocket, versus being not ever connecting with him and being stranded from early on. But indeed, you know, we envision that humans on Mars will land in an area. They will live in another area, and they'll have vehicles and have the ability to transfer equipment to a location to do science, and in fact many locations. And we call that area an exploration zone, and it's about 100 kilometers in diameter. And what we're doing right now is beginning the process of finding those top locations on Mars where we could do that. We have what we call a candidate human exploration site on Mars workshop coming up at the end of Mars. Sorry, at the end of October, and we have over 50 sites that are going to be discussed, debated. We'll then prioritize them. What will happen next is, because we have our Mars Reconnaissance Orbiter, we'll then pick those sites that we want to know more about, that have strong science drivers in the exploration of Mars, and then be able to acquire data from our orbiters. And the Mars Reconnaissance Orbiter in particular, with the high-rise camera, will get high-resolution imaging. And so that just starts the process of really doing a better job of understanding key sites on Mars where we want to do science, and we want to look at the whole planet, and the sites are just all over the place. It's really unbelievable to see what's going to be discussed at the end of October.
So, Bruce, does the response to the movie give us reason for optimism about the public's support or desire to support science?
That's a really hard question. I think we're seeing it's an incredibly popular movie. I think it's one of a series of really good sci-fi movies over the last decade or two. Yep. And I would include Gravity in that. I'd also include Independence Day. There's just a lot of good movies. I think the public is really excited about this, but it remains to be seen whether there's a national will or commitment to exploring Mars, to sending people to Mars. I think there's a strong feedback of the space sciences, the space exploration program, emphasizing now the word exploration, with the public. But it's not easy, it's not cheap, and it's risky.
Yeah, I think one thing that got me about the movie was, you know, and I thought, oh my gosh, there's so much radiation. This poor guy, I'm surprised he's still alive. But that was my, you know, I had read all the other things that said, oh, this was wrong, this was wrong. That was the only one that sort of concerned me, was that, oh, I just thought, oh, wow. And so that's one of the major risks. So what are some of the other major risks about going to Mars, sending humans to Mars?
Well, let's first talk about the radiation, because we actually know a lot. For instance, we have a radiation detector on Curiosity, and so consequently it's made its trip all the way to Mars, it's landed on Mars, it's continuing to make observations, and we're continually analyzing that data. And yeah, there is a significant amount of radiation. You know, the galactic cosmic rays, you know, that's kind of a steady stream of it. The sun can put out all kinds of stuff. Sometimes that can be quite severe. And my understanding from working with the human exploration people is that indeed it does increase the risk of cancer for a full round trip to Mars, you know, a full 500 and some odd day trip there and back to Mars, by about 3%.
Oh, not so bad.
It's not huge, and that also means it's not sometimes one of these really tough storms, but it is indeed survivable. Many of the astronauts would that I've talked to say that's a no-brainer. Count me in. You know, that's even though cancer later in life is something that they face when they go into space, no matter what. In terms of increasing the percentage, and we know about it. There's a lot of research that's being done in that area right now. In fact, just in some recent research that's come out in terms of, if you look at our animal population, there is an animal on this earth that has the least amount of cancer, and it's the elephant.
Right.
Mm-hmm.
Right.
Okay, it has developed mechanisms to identify cells that are reproducing incorrectly and destroying them. You know, so they're not just repairing the DNA, which would be another approach. Sometimes we think that's what we need to do, but you know, the elephant has managed to be able to do that. So I think research is going to continue on in that area. So if we also talk about life, and we say, what about life on Mars? And that's life living in the extreme that has evolved in an environment of radiation, and sometimes intense radiation. What mechanisms have they developed to be able to survive in that environment? We don't know. We haven't discovered that life. You know, if it's there, that's one of the things that we would like to understand. So I think our future is really bright in these areas, and we need to continue on a course of action, making steady progress in our exploration, and that, of course, includes having humans go to Mars.
Okay, and I think Bruce certainly has things to talk about concerning astrobiology, finding life in these extreme conditions.
Well, Jim has talked about the possibility of finding life on Mars. And when I look at the Mars program, or even at NASA's space exploration program, what I see in it is that it's very largely focused on determining whether there is life elsewhere. Right now we have one example of life that we know about in the universe, and that's life here on Earth. It's all one example because we're all descended from a single origin of life or a single common ancestor, and we don't know if there's life elsewhere. We're sending a lot of spacecraft to Mars because Mars is the closest place to us that has a likelihood of meeting the conditions required for life, and that means it's not a stupid idea to imagine that there could be life, and it's a question that's amenable to answering empirically. We can send a spacecraft there, bring samples back, and look for evidence of life. But it's not the only place in our solar system that could harbor life, and now with the discovery of planets around other stars, the fact that they are so abundant, I think over the next decade or two we're going to find a lot of places that could harbor life, and again it's a question of how do we look for evidence for it. I think I'm going to go back to a quote from, I think it was Arthur C. Clarke, who was talking about whether there's life elsewhere, and he said either there is life elsewhere or there isn't. Either possibility would be truly amazing. I'm paraphrasing. If we had even one other example of life in the universe that was independent of the life on Earth, that would be truly amazing. Or if we searched high and low and far and wide and found no evidence and came to believe that we were the only life in the universe, that would be just as amazing. It's really a journey of exploration here.
So speaking as an astrobiologist, give us some context. How significant is water as an indicator?
I think water is probably a necessity. It's really hard, though, to generalize. We know all about life on Earth, but it's one example. And we know what characteristics of an environment are required to support life on Earth, but we don't know if they're general, if they're required for life anywhere. But on Earth, certainly, water's right at the top of the list. You need some sort of a liquid, something through which nutrients can diffuse into an organism, waste products diffuse out. It's very hard to do that if you're in a rock without liquid, for example. And water is a wonderful liquid chemically because it's a polar molecule. It can dissolve a lot of things, and there are things it can't dissolve. But there are other liquids in our solar system. We see methane and ethane and nitrogen-rich liquids on Titan, for example, and we don't know if those liquids could support life. Titan is another example of a place that is worth exploring for understanding the astrobiological relevance. But until we go and look at these places, we're not going to know what the possibilities are.
Well, it's a pretty volatile intellectual field too in the last few decades, right? It seems like as soon as we say this is what is absolutely required for life, we go and we find things in sulfurous vents under the ocean and various other extreme conditions, and we have to sort of keep expanding, which is a good thing, right? But we have to keep expanding our understanding.
I think three things have happened in the last 2 or 3 decades that have fundamentally changed our view about the potential for life elsewhere. One is on Earth the discovery of life living in extreme environments, living in environments that we used to think could never support organisms, temperatures above the boiling point, salinity, pressure, and so on, outside of the range that we normally think of. The second is the recognition that there are places, multiple places in our solar system that meet the requirements we think are necessary for life. And the third is the discovery of planets elsewhere. We certainly thought they existed, but knowing that they're there, having detected them, and getting an idea of now of some of the properties of the planets has really changed our view of the potential for life elsewhere.
So from Jim then, how much does looking for signs of life shape all of our planetary missions in the solar system?
That's a really good question, and I think I want to answer it in this way, and that is we want to start out with a firm definition of life. And that is, in talking to astrobiologists, it has 3 basic attributes. 1, consumes and metabolizes. 2, it reproduces. And 3, it evolves. Okay? So given the question, I want to see if this is life, building an instrument that makes those kind of measurements is really darn tough. Okay? So we then have to say, all right, then what about that environment that we need to look at, that life exists in? Were those things that can be brought together to support the life? And we then change it from looking exactly and demonstrating that this is life to first finding the environments. In other words, we call those habitable regions. So that we can measure. We can measure the materials that are available to determine if there's organics. We can measure if there's water available and in what forms and how it changes over time. And we can measure the energy necessary to support environments. And so our program is really moving in the direction of looking for habitable environments. And Bruce is dead on. You know, Mars has got those. Europa appears to have those attributes. Enceladus, and then of course Titan has liquids, and it's a completely new dimension that would be unfathomable for us 10 years ago to think that life could be in an environment like that. But indeed, we need to look. It really opens our mind as to those kind of environments that could support life. So our program is indeed moving into the direction of habitability. Now that's habitability perhaps also today, but also in the past. You know, the Mars 2020 mission, what that's all about is indeed coring rock, looking at the history of Mars. You know, and as we talked about earlier, Mars in its distant past had huge amounts of water. 2/3 in the northern hemisphere was an ocean. We have measurements, DDH measurements, that indicate that that was the case. And so it had to have an extensive atmosphere, and it had to have, and based on what we measure was there, the environment was much richer environment for the kind of life that was starting here on Earth at the same time. Wow, exactly the same time. And so consequently, those measurements we can make, that's what we go after. And 2020 will core that rock, look at the rock history, how Mars has changed over time, and that will be a huge next step in going after the life question, I believe.
So let me switch gears because we're nearing towards the end of the show. So what we like to talk about on Read Science is, you know, how do we communicate science to the general public? NASA is amazing at this. Now, I don't think I have a specific question, but let's talk about this goal of NASA to inform everyone about the science they are doing. You guys do it very well. So either, both of you, I would love to hear what you think.
I can certainly start out. I think over the years I've recognized that this is such a fantastic field that we really need to bring as many people, and certainly the American public, along with us for the ride. And so having opportunities where Planetary, by and large, can be event-driven. It's not just a launch; it's a landing, it's a flyby, it's a it's some major event that gets where we want to go. And with the right tools and capability to make those measurements, and that's worth celebrating, and that's always exciting because it's incredibly difficult to do. And I think the more we do that, the more we show the public the value for the dollar that they do spend in NASA, but it gives us the opportunity to talk about the science. And it's through the engineering that's also pretty spectacular that enables us to get where we need to go and bring those instruments along to be able to make the measurements we want. That, to me, if I was young and looking for a career and I got caught up in this, I would want to go into these fields. Now, whether that means you're going to end up being a NASA employee or not doesn't matter so much as it is getting, our people educated about what we're doing, getting them involved in our industries, their ideas about new technologies, and I think that's a real economic driver. And we shouldn't. We should really embrace that and take every opportunity we can to bring the public along with us.
And I agree completely with everything Jim said. Let me go a step farther, though. When I look at something like the MAVEN mission, it should be obvious I'm having a lot of fun with it. But we're not flying the MAVEN mission for me to have fun. I might like to think so sometimes, but we're doing it because it's of value to the public and to the whole country. And if we aren't taking the information coming back from the mission back to the public, we're not doing our job. So communications with the public is a fundamental part of doing a mission like this, and I see it as a fundamental part of what NASA does. So I'm happy to come and spend time on a show with you guys today because it's one way to reach the public. I can do public talks, I can do interviews, I can write for the public, but we need to figure out the best ways to effectively communicate what we're doing. And it's not that we're trying to convince people they should come to work for NASA or give us more money. Those are all nice things, but we're doing it because it's an imperative that the public who's paying for it and at whose behest we're doing this get something back from it, that they understand what we're doing and why it's valued and why it's an activity that should continue. In our current political and fiscal environment, it's hard to justify spending money on things that aren't a true necessity. So it's important for us who understand why it's important to explain to the public and to interact with them on what's important and why.
Both of you have used the word before, and it was, for me, I thought, a central theme in your book, Bruce. The idea of exploration as a fundamental human drive, and that we see science as an exploration. And I was going to ask something that was related to exploring and doing these things. Well, anyway, I know the point I wanted to make is that when I was talking to the press sometimes about our microgravity science, which was pretty loosely related to cures for cancer or Teflon coatings for things, the questions that I kept getting always seemed to be about what could develop from something, what product might come up. And I was pleased that in your book, and I'm happy to hear Jim talk about this, that it's nice when I think people are able to say we're doing this mission, we're exploring these planets because people explore. It's a fundamental aspect of what we are. We have to learn. Who knows what's going to happen, but we have to explore, and that is really one of the foundational reasons that we do this. I like to hear that. So thanks.
I think
but is that true? What is that thing about exploration? You know, why do we do it?
Well, we plan on learning something. And every case, we are astounded by not only what we learn, but what we didn't know and what we need to know. And I see that over and over in our missions. We set out with a goal of answering tough questions, and we uncover new ones that are just equally exciting. This is what knowledge is all about. This is the process that we use as humans to be able to acquire that knowledge, and that is really focusing our attention on the tough questions and getting the answers, and that leads us to more inquiry.
And Jim is absolutely right about the importance of asking questions and getting answers, but I see that as a means to an end, not the end in itself, because the end, in my view, is really addressing this drive we have to understand the world around us and to understand how we relate to it. We're interested in exploring Mars and the other planets because we live on a planet. We want to understand what makes the Earth special. Why is it significant? What other outcomes could have been possible? And to my mind, we're interested in the search for life elsewhere because, well, gee, we're life, and we want to understand how special or unique we are. What are the conditions that led to life? How widespread is life? Could there be intelligent life elsewhere? And by understanding these things, we're really understanding how we relate to the world around us, how we as individuals, as a society, as civilization, as human beings relate to the world around us. And to my mind, it gets back to understanding what it means to be human. And understanding who we are. So it really comes back to what we are and how we relate to the world around us.
So we explore as a fundamental, as a way to understand ourselves, which seems to be a very fundamental sort of need. Yeah. Well,
we indeed do science when we explore, and we really explore to survive. That's what the pioneers did. That's what we continue to do, whether it's in the depths of the oceans or out into space. The more we learn about our environment, that the Earth is orbiting the sun, and it's not a benign area. The dinosaurs, as we all say, didn't have a space program. The moon, the pock marks on moon are not volcanic; they're impacts. And so these things we've learned in just a lifetime. And so this is really critical, I think, for us to continue on our quest of really understanding our environment on Earth, but Earth in general around our sun and what will happen over time. You know, what's happened on Venus could happen on Earth.
Yep.
What's happened on Mars could happen on Earth. You know, we have a snapshot of time in the evolution of these planets. And how rapidly do they change? We have a wonderful opportunity because we have terrestrial planets sort of like bookends. You know?
That's right.
We now know that the sun is going to change over time. Well, how does that change the habitability in and around the Earth? And it will. This is just, I think, critical knowledge for the survival of our species. And the more we recognize that, the more we then can, I think, continue on in this direction and make steady progress. We have to.
So in part 2 of this conversation, Bruce will be addressing the question of a better way to teach science, which sounds to me like you're suggesting, and I believe that it's true, we should expose it to people as an exploration and not as a body of facts.
Absolutely. We tend to teach science as a collection of facts. If you look at any freshman science class at the college level, that's what they talk about, that's what they teach, that's what they test. But really, the fundamental tenet of science is that the world is inherently understandable, and you understand how it works by observing how it works and applying basic logic and physical thought to it. That is a whole nother discussion.
Yeah, that's why Jeff said part 2. Oh, quickly before I give you guys a chance to say last words, I do. The movie The Martian was equal parts how is he surviving, and equal parts how is NASA going to tell the world what happened. We left someone up there. Actually, he's alive. Whoops. And then how are we going to get him? And I saw that. Bob Jacobs, sorry, I'm out of focus for some reason. Bob Jacobs, who is communications director for NASA, was one of the consultants, and I thought that's interesting because it went beyond just the science that NASA is known for. It also involved the communication that NASA is known for now.
Part 3 will be science in society. Yeah.
So indeed, what I really liked the movie is in many ways it captured aspects of our culture. Mm-hmm. You know, the Hermes crew, including Watney and including the ground controllers, including Mitch, were all a team. They were a team, and a solid team. There was no fighting between them or tension. You know, NASA's not going to put people on Mars that are going to do nothing but fight each other, you know? So that rings true. It doesn't need that for dramatic accuracy, because it's not, you know? Another thing is each of the problems that were presented to various levels within the agency, each of those people came with a different opinion. You know, the administrator is looking at, I don't want this on the front page of the Washington Post. Well, I've heard that before. That's sort of been my environment. And so that's a perspective, you know. Also, when Vincent Kapoor goes in and talks to Teddy, the administrator, and says, "We need, give me permission to image that area," and he says, "No, because I don't want a dead astronaut on the front page of the Washington Post," I knew exactly what Vincent was going to do, because I've had conversations for which I've been challenged, and you go right through the logic. This is why we need to do that, and that's what convinces Teddy to finally allow Vincent to task the orbiters to get high-resolution imaging. So, so much of the parts about headquarters rang true. I could identify people in the agency that have those responsibilities and indeed have perspectives that have to be respected and brought in. So the movie has a lot more than just the science. It's really a human story.
Right.
And the fact that it rings true to the nature of our business and what NASA does is one of the real key reasons why I really wanted to help Ridley in painting the right picture.
That's fantastic. Yeah, I was really impressed all the way around. So we are at the top of the hour, and what we like to do is to make sure our guests don't leave unless they've said everything they want to say within reason. So if you have a parting thought that you would like to leave with our audience, feel free. We'll start with Bruce.
Mars is exciting. That's all I have to say.
You've dedicated your entire life to Mars, so you're a living example.
Maybe my entire work life. I'm hoping not my entire life, and I'm hoping it's only my life so far.
Still, plenty of time. Yes, Jim.
Well, I've told a number of people in the community this, and that is, I want to be the director of planetary science when we find life beyond Earth. So they better get busy.
Yes, the clock is ticking. It still ticks. Jeff, anything you want to say before we say goodbye?
No, it was exciting talking about these things, and there's so much more to explore. But we've made a really good start, so thanks very much, Bruce and Jim, for the lively discussion. I really appreciate it.
Yeah,
thank you.
Thank you.
Yes, thank you for joining us, and thank you to the audience for joining us. We've enjoyed your company, both Jim and Bruce. Indeed, a lively conversation. I really enjoyed it. And to everybody in the audience, appreciate you tuning in, and we will see you again on another episode of Read Science.